Morning, guys. Okay, before we start, any comments, suggestions for the class? Is that too slow or too fast, or you feel that's okay?
I feel like I'm doing pretty okay right now.
Yeah, that sounds good. I mean, I know that in the beginning, most of the contents will be just introduction. So later on, there will be more, a little bit more derivations. So if you have any questions or want me to slow down, you can always say so, okay? You can type in the chat or in the class, you can just raise your hand, right? I have to say that there isn't a lot of mathematical parts in this class because as you know, this class is an elective class, right? So I really don't want to put too much of the mathematics into the class, but there are a few equations that we need to understand. So I would say that when we get to those contents, just let me know if you have any questions. Okay, so it's already 10 and we can get started, okay? So this class, we're going to just carry over from the discussion on the size distributions. So first, let's do a recap again, okay? So last class, we mainly discussed the importance of the PM. So we said that the PM is important because not only because it's climate impacts, right? The most important thing is still on the human health. But what's quite surprising is that the particles, not all of the particles are depositing onto our lung surface, like on the cells, right? There is actually a quite special shape of the deposition curve. Right? It has a U shape, but eventually it's going to drop down. And there are a few specific sizes, and especially for the lowest deposition efficiency point, it's around 0.3 micrometer, okay? So the reason for this shape is that mainly for the larger particles, they can just deposit through the impaction or interception. And for the smaller particles, they can deposit through diffusion. And actually, it's the particles that's in the middle range that are most difficult to deposit onto our lungs. And the same mechanism is being applied onto the masks, right? So that's why the N95, its efficiency is being evaluated at 0.3 micrometer particles. Because we know that if the efficiency of the mask at this special size is above 95%, then pretty much we don't need to worry about the other sizes because they can easily get deposited onto the mask materials. So some of you may also have the question, right? So I think if you recall the curve that we showed the other day, right? The surgical masks and the cloth masks, they're not having as high of an efficiency compared to the N95, right? I just write it out, surgical or cloth. More specifically, we mentioned that the size of a SARS-CoV-2 virus is around 0.1 micrometer, okay? So then you may have a question, well, does that mean that we're not safe with the surgical mask or cloth mask? And as a matter of fact, for the SARS-CoV-2 virus, there isn't a virus that's just suspending in the air in its naked form, okay? Although that we know the virus is a coronavirus, right? Has the corona, or has these spikes on its surface. But the thing is that when people emit these viruses from coughing or from speaking, it's not only the virus that we're emitting out, it's actually a chunk of materials, right? There are some proteins, right? And there are salts almost everywhere, right? We know that there's sodium chloride in our saliva. So compared to the volume of these components, the SARS-CoV-2 virus is very small. And what actually happens is that the average size for the aerosols that's emitted through speaking or coughing has a size that's above 10 micrometer, okay? So the 10 micrometer is much, much larger than this 0.3 micrometer, which means that they can easily get collected onto the mask material, okay? So that's why the mask is so efficient in blocking the virus or capturing the virus and stop the transmission, right? Then after the discussion on the mask, we mentioned about different sources of the PM, right? We said that there's a top-down approach and bottom-up approach. So top-down approach is basically tearing the materials apart, right? So for example, when we're emitting these coughing aerosols, or when we're doing the machining process, like sawing or grinding, right? So we can generate these particles by tearing the original materials apart. So there's also the bottom-up approach, which is assembling these particles from the vapors or from the molecules, right? So that's also quite common. For example, combustion process, right? And then we can also have, like, let's say, the engine emissions and so on. So then we talked about the important parameters of the aerosols. So we mentioned that both the concentration and the size are very important, right? Concentration can include mass concentration, number concentration. The size, we also have different metrics. But since size and concentration are so important, people created a term called the size distribution. Basically, it's just a distribution of particles with different sizes, right? So the size distribution is going to contain both the size and the concentration of the particulate matter. And after that, we discussed how we can measure the particle size distribution, right? So that's being measured, or more conventionally, it's being measured with a cascading impactor. So you can think of Cascade Impactor as a size cutter, right? So basically, if we have any stage of the impactor, based on its geometry and based on its flow rate, it's going to provide a cut size that only allow particles smaller than this cut size pass through, right? For example, if this stage has a cut size of 25 micrometer, then all the particles that's smaller than 25 micrometer can pass through, right? Well, for the particles larger than 25, they can get deposited here. And because of that, we can design a second stage, let's say, to have a cut size of 10 micron, so that particles between 25, say dp smaller than 25 and larger than 10 micrometer can get deposited in here, right? And here we can have a stage that has a size of 5 micron, right? Which collects particles smaller than 10 and larger than 5, and so on and so forth. Okay, so once we have the mass of the particle, so basically we can, after some time of sample collection, we can take out this stage here, measure its mass, right? We can get the delta mass, basically the mass that's deposited on different stages of the impactor, right? So in this way, we can get a distribution of sizes, right? For example, 2.5 to 5, 5 to 10, 10 to 25, and so on, right? So if we show the delta mass here, they might have the curve that looks like this, right? Or the shape that looks like this. So we can call this a size distribution. And basically, this is also how people determine the concentration of the PM in the air. Let's say the EPA standard, right? When it measures the PM 2.5 or PM 10, right? So they can just measure what is the mass that's getting deposited onto the stage here, and then just add them together, right? For example, here it's collecting particles. Here on this stage is collecting particles below 10 micrometer, right? It's one part of the PM10, right? Here it's collecting particles from 2.5 to 5. So eventually here, we're going to add a filter, okay? So filter is going to collect everything. Just think about the N95, right? You can collect all the remaining particles. So here we're also going to get a delta mass, right? So in this situation, the PM10 is just going to be delta M1 plus delta M2 plus delta M3, right? It's particle mass below 10 micrometer, or below 10 and above 5, and below 5 and above 2.5, and everything else, right? So this is how we can get the PM10. So then you may have the question, well, we're just getting an absolute mass. How do we convert that into mass concentration, right? So that's also pretty straightforward, because let's say that we have this impactor here and it's operating at a flow rate of 10 liters per minute, right? We can control the flow rate through this device, and we maintain that at 10 liters per minute, okay? And then what we do is that we can sample it for, let's say, 1 hour. So what we know is that during this 1 hour, the total volume of air that's going through this device is going to be 60 minutes multiplied by 10 liters per minute. That's 600 liters, right? And let's assume that we get this PM10, let's say this total mass, to be, for example, let's say 60, right? For example, what the mass that we eventually measured is 60 micrograms. Then we can just directly calculate the mass concentration, which is 60 micrograms, divided by the total volume, 600 liters, right? We further know that 600 liters is 0.6 meter cubed, right? And then this is still 60 micrograms. And you can find out that the final concentration is 100 micrograms per meter cubed. Okay, so this is how we can use the impactor to measure any concentration of the PM10 or PM2.5. Okay, so then we can continue to discuss the size distributions. So you can see that with the impactor, we're able to get a distribution of particle sizes, right? But there are some limitations. So we call these types of size distributions as the discrete size distributions. So by meaning discrete, what I mean is that it seems to show that the concentration of particles, let's say of 3 micron and 4 micrometer are the same, right? With this discrete size distribution, what that means is that the mass concentration of the 3 micrometer particle is the same as the mass concentration of 4 micrometer particle. And we know that in the ambient air, it is not the case, right? Because there isn't such an air that if you just collect all of the particles with the same size, right? 3 micron and 4 micron, they happen to have the same mass concentration. That's very rare. So what's more likely to be happening is that the size distribution in the air is going to have this bell-shaped curve, okay? So that's why people also come up with the size distribution that has a continuous form. So if we still plot dP and mass concentration, right? So instead of having a discrete size distribution, so the ambient air is more likely to have this continuous size distribution, okay? So it's also easier for people to do some mathematical calculations, right? Because if you have the discrete size distribution and you want to measure what's the concentration below 4 micron, right? It's a little bit difficult to do this calculation. But if you have a continuous size distribution, what you can do is that you can directly integrate, right, to get the total concentrations here, right? So basically, with this new assumption that the size distribution of the particles is going to be a continuous, is going to have this continuous form, then people start to think about what are the mathematical ways to better show these size distributions, or mathematical expressions, right? So let's try to use mathematical expressions to basically show these size distributions. So I guess that the first mathematical equation that we can think about right now is the Gaussian distribution, or people also call that normal distribution. It is quite straightforward, right? Because if you recall, the normal distribution is going to have this bell-shaped curve, right? It's going to have a highest concentration in the middle, and then the concentration is going to be lower, or the values are going to be lower at the two ends of the distribution. And this is indeed what people first came up with. Okay, so they came up with the Gaussian distribution to approximate the size distribution of aerosols in the air. So the Gaussian distribution is going to have the form of m total divided by sigma square root of 2 pi, and then exponential of minus dp mean okay. So this is the equation of the Gaussian distribution or normal distribution. And I think you probably have already taken this class when, let's say, when you get the undergrad mathematics, right, statistics, right? So this is a pretty elegant way to show the continuous size distribution. But there are two problems with this equation, okay? So the first thing is that there's going to be a point that, or a range that is doesn't make sense at all, okay? So what I mean is that if a particle has a size that's below 0, if a particle has a negative size, okay? If you plug this value in, you can find out that the mass concentration is still positive, okay? So this is not nice at all, right? For example, if we do some calculations to integrate, let's say to integrate the concentration of the particles, and then we have to exclude the particles below 0, right? But the thing is that with the Gaussian distribution, it's still going to give you a positive concentration, which doesn't make sense at all, right? So the second thing is that for Gaussian distribution, when we show the particle size, it's going to be on a linear scale. So what I mean is that basically, if we plot the mark the x-axis, okay? For example, here is point, let's say that here is 10 nanometer at this point, and this is 11, this is 12, 13, 14, right? Nanometers. But the thing is that we know in the air, there are particles of all different sizes, okay? There may be even particles of a few microns. As we said, when we cough, we generate particles of 10 micrometer particles, right? So how do we plot those particles on this curve here? So if we want to show everything on this Gaussian distribution, what we're going to have is basically a high peak in the nanometer range, and then relatively few particles in the micron range, right? So basically, with this form, it's going to be very difficult to show the tail of the particulate matter, okay? So basically, with this Gaussian distribution, it's going to be very challenging for us to both show the particles of nanometer range and particles of micrometer range, okay? If it's in millimeter range, it's further difficult, right? It's more difficult. So these are the two problems, but how do we overcome it? Okay, so people actually came up a method or a mathematical way to better show the size distribution, and that's what we call the log normal distribution, okay? So the log normal distribution is still very similar to the normal distribution, except that we show the particle size in the log scale, okay? So we're converting this x-axis into log, right? So basically, if it's in the log scale, then we're going to have the new mathematical expression of M total. So most of them are actually quite similar. Okay, so this is the equation for the log normal size distribution. And you can see that actually a lot of the components are the same, right? You have the M total, which is the total mass of the particles, right, on the numerator, right? And then you have the square root of 2 pi, right? You have the sigma g, which is the standard deviation, right? And then in the exponential term, you also have the squared and also the sigma g in the denominator. Okay, so a lot of the terms are the same, but there are some advantages of using the log normal size distribution. Okay, so it's better compared to the normal distribution on these two aspects. So if you first look at particle of negative size, so in the log normal size distribution, can we still have negative size particles? No, right? Because if you notice here, the particle size is now in the log form. So by using the log form in the distribution here, it naturally excludes the condition where the particle size is negative, because for the log of dp, it doesn't make any, it doesn't carry any meaning if we have a particle that has a negative size, right? So it naturally excludes the condition where the particle size is negative. So the second thing, right, about the tail. So the advantage for using log normal size distribution is that now we can show particles of 1 nanometer, 10 nanometer, let's say 100, 1000, let's say nanometers, or 1, 10, 100, 1000 micrometers, everything onto this same plot. That's mainly because if you take the log, so all of these, right, if you take the log of 1 nanometer, right, 1 nanometer, we know that it's 10 to the negative 9, right? So you're just going to get negative 9, negative 8, negative 7, negative 6. And for micrometers, that's negative 5, negative 4, negative 3, right? So we convert this particle size of orders of magnitude difference into a new linear scale, right? So what I mean is that now, if you plot the log normal size distributions, you're just going to have, let's say, 0.001, 0.01, 0.1, 1, 10, 100. Okay, let's say we plot it in micrometers. Okay, so basically with this log normal form here, we can start to plot everything, right? Particles of all different sizes onto this same plot, right? So these are the two advantages of using the log normal size distribution. And also by using this more elegant way of showing the continuous size distribution, we can do some more mathematical derivations. And that's why people like these size distributions. And as a matter of fact, if you just measure the air or aerosols in the air, right, you can see that most of these size distributions actually satisfy this log normal size distributions. So there may be something that's off, right? Let's say 10% off at certain size, right? And also you might not have this very continuous form, but in general, let's say you do the average or do the smoothing, then you can find out that they generally agree with this log normal size distribution. Okay, so this is to show the size distribution in the in this concentration form, right? So people also like to show the log normal size distributions, or to show the size distributions in the cumulative form. Okay, so what the cumulative form means is that let's start to calculate what is the cumulative fraction. Cumulative fraction of particles below certain size. Okay, so what I mean is that, let's say if we have a particle size distribution that looks like this. Okay, let's assume that this highest peak is at 1 micrometer, and then you have 0.1, you have 10 on both sides, and then 0.01 and 100 on both sides. So I'm plotting the size distribution in the log form, right? So what the cumulative mass fraction means is basically we pick up any size. For example, just at 1 micrometer, okay? We do the integration of the particle concentrations, and then we divide that by the total concentration. Okay, so total concentration is here, right? So you can find out that basically the cumulative mass fraction, or the cumulative size distribution at 1 micrometer, specifically for this size distribution, is going to be 50%, right? Because you see that the highest peak or the highest point is corresponding to 1 micrometer. And if you do the integral of everything below 1 micron and divide that value by the total concentration, you get 50%, right? So we can do the similar thing, right? For example, we're trying to calculate 0.01, right? So you see that it's going to be something here, right? We'll use this area to divide the total concentration. And for example, let's assume that this value is 2%, okay? It's going to be very small. If we look at the concentration at, or the cumulative fraction at 100 micron, right? So we're looking at this point. Then the cumulative mass fraction is going to be everything below this size, right? For example, let's assume that it's 98%. So basically, if you plot the cumulative fraction as a function of size, we're going to convert this size distribution into a cumulative fraction curve that has a shape of an S, okay? So basically, at 1 micrometer, you're going to have 50% of the mass fraction, okay? At 0.01% of micrometer, this is 2%, right? And then at 100 micrometer, this is 98%, okay? So this is how we can show the cumulative mass fraction. So why is it important? Okay, so it turns out that people actually use these cumulative mass fractions to tell whether a size distribution is log normal or not. Okay, so this is a relatively easy way to tell if the size distribution or if the PM follows log normal distribution. Okay, so then you may have the question, well, it just looks like an S, right? So how do you tell whether this is log normal or not? Okay, it can be any S, right? It can be something that looks like this, right? Or something that increases a lot and then just taper off, okay? So actually, the method that people came up with is basically make some revisions, make some modifications onto this curve here. Okay, so if let's say that if we further track what is the cumulative mass fraction at 0.1 and 10 micrometer. So you can see that at 0.1, this is still relatively low, right? It's somewhere here. And then at 10 micrometer, it's pretty high at here. Okay, so what people do is that they actually squeeze. So you can see that right now for the cumulative fraction, it's still using a linear scale, right? So what people do is that they actually squeeze the distance between, let's say, 50 and 60, 40 to narrower. Okay, they squeeze the distance between these different markers to a narrower distance, right? Instead of having 60 at this point, we start to have 60% at this point, okay? Instead of having 40% at this point here, originally, we now start to have 40% that's closer to 50%, right? So we squeeze all of the markers that's close to 50%, but at the same time, we stretch the distance that's away from the 50%, okay? We stretch the percentage or the values that's close to 0% or 100%. So instead of having 2% at here, we're going to have 2% at here, okay? Instead of having 98% in here, we have 98% at here. Okay, so basically what we eventually achieve is that we're going to have this new point, let's say at 0.01 micrometer is corresponding to 2%. So the new 2% is at here, right? Then we're going to put the point at this location. And at the same time, in this newly stretched curve here, we're going to have 98% at here. So eventually what we have is that if this cumulative fraction falls on a straight line on this curve, then we can tell that it is a log normal distribution. So basically what I mean is that people start to use this table, what we call the Semilog plot. Okay, so on this Semilog plot, you can see that the particle size follows a log normal scale, right? You have the 1 micrometer here, 10 micrometer here, 100 micrometer here, right? But at the same time, in terms of the fraction, you can see that the fraction values close to the middle are narrower, right? While at the same time, the fraction values that close to 0% and 100%, they're stretched, okay? So on this Semilog plot, for example, if we plot any size distribution, okay, and if they follow a straight line, okay, then we will say that it follows the log normal size distribution. So we can do an exercise with this plot, okay? So basically, this is the example problem on your textbook. Okay, so first we can take a look at the problem, right? So the following data were obtained from a Cascade Impactor, okay? And it measures the, basically measures the particle size distribution. It can measure the mass of particles between different sizes. Okay, as a matter of fact, you can see that it is indeed the case, right? We measure the particle mass from 0 to 2 microns, and the mass is 4.5 milligrams, right? 2 to 5 microns, 179.5, right? And then 15 to 25 micron, this is 73.5, right? So basically, we're using this Cascade Impactor and then just to measure the mass that's collected onto different stages according to their cut sizes, okay? And then what it wants us to do is that it wants us to confirm this size distribution is log normal and find what is D50 and sigma G. So D50 here is just the geometric mean size, and sigma G is the geometric standard deviation. So you remember earlier when we showed the mathematical equations, right? The DPG and sigma G are basically the two important parameters of the log normal distribution, where the DPG is basically the mean size and sigma G is the how spread, right? How spread the size distribution is, okay? So actually you can find out everything just with this log normal size distribution or just with this Semilog plot. So the way we do this is we need to first convert this size distribution into cumulative mass fractions. Okay, so the way we do that is first, we're going to label out all the different sizes, right? 0 to 4, 0 to 2 micron, 2 to 5, 5 to 9, 9 to 15, and 15 to 25. Okay, so at the same time, let's just label all the mass that we collected onto these different stages, right? 4.5, 179.5, 368, 276. Okay, so these are the mass values that we collected onto different stages. And then we can calculate what is the mass fraction in this size range. Okay, so the way we calculate this fraction is just divide this value by the total mass. Okay, divide that by 920. And you can find out that we're going to have the mass fractions corresponding to each stage, right? So the cumulative mass fraction or the cumulative percent less than the top size is just going to be basically this value here. Let's say for 2 micrometer, it's just going to be the same as the first stage, okay? This is close to 0.5%, right? And for the second stage, because here we're talking about everything below 2 micrometer, right? The percentage of particles below 2 micrometer, that's just 0 to 2, right? It's going to be 0.5%. And if we talk about below 5 micrometer, then we have to add this 0.195 with the 0.5, right? Because 0.195 is just everything between 2 and 5. Well, in order to calculate below 5 micron, we need to also consider this range here. And this is 20%, okay? And then here is going to be 0.4 plus 0.195 plus 0.5 or 0.005. That's 60%, right? And then this is 0.3 plus 0.4. That's 90% and so on, okay? So this is how we can calculate the cumulative mass fraction. This is just by adding the mass fraction in different stages together, okay? So then you can basically find out what is the mass fraction, the cumulative mass fraction corresponding to each size. And now we can start to label all of these points, okay? So what this basically means is that we need to find out the size that's corresponding to this percentage, right? The size corresponding to this percentage is 2 micron. The size corresponding to this percentage is 5 micron. And here is 9, here is 15, here is 25, right? Because when we talk about cumulative mass fraction, we're talking about everything below this size, right? Everything below this size. Okay, so now we can start to label all of these data points here. So first, let's find out 2 microns. So 2 microns are going to have a cumulative mass fraction of 0.5. So first, let's find 2 microns. This is on the Y scale, right? And then we just need to look for 0.5. So 0.5 is between 0.2 and 1. We can just label it at here, okay? And then it's the 5 micron. So 5 micron is corresponding to 20%. So we can first find 5 micron, and then 20% is here. Okay, 5 micron and 20%, right? And then we have 9 micrometers, right? 9 micrometers at here is corresponding to 60%, right? It's here. Okay, and then 15 microns, that's 90%. 90% is here, and 15 is at here. Okay, and then 98% corresponding to 25 micron. So it's going to be somewhere here. Okay, so now if you look at all of these data points, they actually follow a straight line, okay? So basically, this is how this Semilog plot is useful. So it can tell you whether size distribution does follow or does not follow a log normal size distribution. For example, if we happen to have a distribution that looks like this, right? Then we know that it's not going to follow a log normal distribution, okay? So actually, with this Semilog plot, we can find more interesting information or more important information. So what I mean is that we can simply use the particle size at 50%, okay, to find the geometric mean, basically the mean size of the particle size distribution. And further, we can find the percentage that's corresponding to the values of. So we can further find the percentage that's corresponding to the value of 84.1% and 15.9%. So for these two percentages, they're going to correspond to the size of dpg divided by sigma g, and this is dpg multiplied by sigma g. Okay, so basically for particles of these two different sizes, they're always going to have the percentage of 15.9% and 84.1%. Okay, so why is it? Right, so it seems that these are all the properties of the log normal size distributions, no matter what, or no matter which curve they're going to follow. Okay, so for example, if we have a curve that looks like this, right? And then we can tell that the dpg is just, let's say, 18 micrometer. And if we find the 84.1, so for example, the size is 40, then that means that the 40 is equal to dpg multiplied by sigma g. While at 15.9, let's say, then 8 micrometer is going to be dpg divided by sigma g. Okay, so this is the property of any log normal size distribution, and we can simply derive that with some equations. Okay, so the way we can derive it is going to tie back to the log normal size distribution. So basically, we already show that the log normal size distribution is going to have the form of m total divided by square root of 2 pi dp log of sigma g, and then exponential of minus log dp squared. Okay, so this is the size distribution that we discussed. Okay, dp and m. So how do we calculate the cumulative mass fraction? Right, so the way we calculate that is we will integrate the size distributions and divide that by the total mass, right? So we can actually calculate this integral. FdP is just going to be the integral of 0 up to, let's say, dp, right? Any size. And then m dp, d dp, and then divide that by the m total. Okay, so this makes sense, right? So we just integrate this size distribution below the size of dp, and then divide that by the total mass. Okay, so what people find out is that for the log normal size distribution, it has a very special property. So basically, after you do the integral, you can find out that the answer is very simple. So the answer is just 1/2 multiplied by 1 plus the error function of certain terms inside. So the term inside is just log of the dp, the capital dp, where it's the size that we are interested in, right? Divide by the mean size, the dpg, and then further divide by square root of 2 log of sigma g. Okay, so we can further find out that actually when the particle size is equal to these 3 different special sizes, for example, when the capital dp is equal to dpg, which basically means that when the particle size is equal to the mean size, if we plug it in, you can find out that this is just 1/2 plus the error function of log dpg divided by dpg square root of log sigma g, right? So this term is just 1, right? Log of 1 is equal to 0. So actually, the error function of 0 is also 0. So this is just going to be 1/2, which is 50%. So this means that if we have the particle size that's equal to the mean size, I say the geometric mean, at this point, the cumulative mass fraction is always 50%. Okay, so we can also plug in this size, right? dpg multiplied by sigma g. You can see that if the particle size is dpg multiplied by sigma g, right? This thing is just going to cancel out, right? This is going to be log of sigma g, and this denominator and numerator can cancel out, right? So it's just 1/2 multiplied by the error function of 1/square root of 2. Okay, so this happened to turn out to be 84.1%. Similarly, for the dpg divided by sigma g, that's 1/2, 1 plus error function of -1/square root of 2. It's 15.9%. Okay, so basically, if we plug in this size here, it's the same, right? Plug in, this is divided by sigma g, and log of basically a 1/sigma g is just going to be the negative of log of sigma g. Okay, so we can get the similar answers here. So basically, with these 3 special sizes, you can see that the cumulative mass fraction is going to carry the same values. All right, so this is a special property of the log normal size distribution. And how does it reflect in our Semilog plot? Okay, so this is another example on your textbook. So basically, it's telling us the particle size distribution is already log normal. Okay, we already know that. It has a dp50 of 6 microns, right? 6 micrometers, which means that the mean size is 6, right? And sigma g of 2. Okay. It wants us to plot this size distribution onto this Semilog plot and determine the mass percent of particles below 2 microns. So how do we do that? So with these properties, we can start to do our plotting, right? So when dp is equal to 6 micrometers, we know that the fraction is going to be 50%, okay? So we can just find the 6 microns on the y-axis and 50% on this plot here. And this is one of the data point, okay? And then when dp is equal to 6 multiplied by 2, right? So basically dpg multiplied by sigma g, right? That's going to be 12 micrometers. And for this size, it's going to have the percentage of 84.1%, okay? So we can just find 12 micrometers, and then 84.1, that's going to be here, okay? And then for dp equal to sigma or dpg divided by sigma g, that's 6 divided by 2, which is equal to 3 micrometers. That's going to have a percentage of 15.9%, right? We just need to look for 3 microns, and 15.9 is here. And this is how we plot the size distribution. We just need to draw a straight line. Okay, so this is a size distribution. And then it's asking us, what is the mass percentage of particles below 2 microns, right? That's going to be very straightforward, because this is showing the cumulative mass fraction. So we just need to look for 2 microns, right? And that's just going to be 5%, okay? Because this point is corresponding to the percentage of 5%, right? So this is how we can use the Semilog plot to do the calculations for particle mass fractions or the cumulative mass fractions. So I think for the homework that's due next Wednesday, you also need to know what is the removal efficiency. So basically the removal efficiency is just it's just the percentage of particles that's getting removed divided by the total concentration, right? So this concentration can be number or it can be mass. Okay, so you just need to understand this simple concept. So if you want, you can also go over this example 3.1. It is quite easy to understand, right? So we won't have a class on the upcoming Monday. So the homework is directly due on Wednesday. But if you have any questions on the homework, we also have the office hours, right? On Wednesday and then also Tuesday night at 7 p.m. Okay, so just let me know if you have any questions.
Have a good weekend.
Yeah, you too.
Thank
Have a
you.
nice weekend, guys.